You are ready to go, eh? Okay, so our next speaker, hang on one second. Yes, Tim Trudgian from UNSW, University of New South Wales, Canberra. Don't believe the fake news. Please.
Yeah, thanks very much, Mel. Good morning and or evening to you wherever you are. I have zero intention of sharing any slides. I'm just going to tell you a bit about my paper. It's always awkward with an online conference because I have no idea, is anyone there? Does anyone care? Is anyone listening? So if anyone did want to turn their cameras on, at least then there's the veneer of maybe some people are listening. Maybe, I don't know. Anyway, thank you very much, Mel, for organising. Kevin O'Brien's in the house. How you doing, Kevin? Yeah. And Carl Pomerantz. Oh, it was always good. Always people coming up. Wow, it's exciting. Yeah. Well, now that I can see Carl, let me say 2014 CNTA. I remember Carl Pomerantz gave the last plenary talk of the whole conference. And it was deep into the conference. It was day 5. The coffee and the donuts had worn off and everyone was tired. And Carl gave, I think, one of the best talks I've seen where he more or less said, look, I've got to go easy on you guys because it's been a long day. It's been a long conference. So we're not going to have lots of fancy notation. We're not going to have lots of fancy words. We're going to have fancy slides. We're going to just have a discussion about these ideas and hopefully we get somewhere. Maybe we do, maybe we don't. So thank you very much, Carl. I do remember that talk well. And this will be in that kind of style where I hope to flesh out some of the points of this article that I wrote with, with Mike Mossinghoff and Greg Martin. But before I do that, I wanted to thank Mel Nathanson again. I know that you guys wanted to have an in-person conference and didn't turn out this time. If you had one, maybe I would have come from Australia, maybe not. But I really, for those people who have organized conferences before, we all know how good it is to see people in person. For those who haven't organized conferences before, it's a lot of work organizing a conference. And Mel's put all these talks up, all these abstracts up. It's really a lot of work that does go appreciated. I remember watching the talks last time from the last CANT. And this is my 3rd talk in New York at 5 a.m. Canberra time, 6 a.m. Canberra time, now 7 a.m. Canberra time. I used all my combinatorial and additive number theory to make sure this talk would be at 7 a.m. Hooray for me, yeah. They gave me that PhD. They can't take it away now. And thank you also to the other speakers. I'm very sorry. I will be seeing 0 talks live. I'm in my spare room at the moment, which is also my son's music room. They'll be barging in any minute now to be doing music practice. So the timing doesn't work out so well, but I made my own talk. So, you know, what do you want from me? Yeah. So thank you, everyone, for coming. Thank you, Mel. Thank you to the other organizers. And sorry that I can't see these other talks live. I will watch them when they go up online, though. I will. So what do I want to talk about? Well, this is a problem that I looked at, I guess, the first year I was a PhD student. So I started in England in 2006 in Oxford. And one of the first books I read, I had done almost 0 number theory before I started there, almost 0. And I rather suspect that Roger Heath Brown, my supervisor, was a little bit disappointed that I didn't know anything. So he said, I guess you better go read some books and know something. So one of the first books I read was Ram Murthy's book, Problems in Analytic Number Theory. And there I saw this business of the so-called Polio Conjecture and the so-called Tehran Conjecture. So what are those? Well, they both have to do with Liouville's function. This is this lambda of n, which counts +1 if n has an even number of prime factors counted with multiplicity, and -1 otherwise. So lambda of n is completely multiplicative. It just flips between +1s and -1s. And I'd never seen this result before. Like, I'm sure everyone else had seen it before, but I hadn't seen this result before, where you connect a proof of the prime number theorem with a proof that you get some cancellation when you sum up the lambda of n's. Sometimes there's some +1s, sometimes there's some -1s. You expect some cancellation. There is some cancellation, and that's equivalent, thanks to Landau. He was a clever fellow. He was always proving stuff. That's equivalent to the prime number theorem. So these so-called Tehran conjecture, this so-called Polio Conjecture, that's saying what? It's saying, okay, sure, I can take sums of these plus minus ones, and sometimes the sum can get big and positive, sometimes it can be big and negative. Okay, fine. But the so-called Polio Conjecture is to say, well, let's just do it. Let's just look at some values of lambda of n. Well, lambda of 1 is 1, and that's true. And lambda of 2 is minus 1, and lambda of 3 is minus 1, lambda of 4 is plus 1 because 2 appears twice. So if I take their partial sums, I sum up n up to x of lambda of n, then apart from, say, x being 1 when the sum is 1, and x being 2 where the sum is 0, all future points, it looks to me, it looks like all future points are less than or equal to 0. Like if you just do it yourself, you sum lambda of n up to 10, say, and it's less than or equal to 0. I don't know what it is, but it's non-positive. So Polio's so-called conjecture is to say, all right, look, maybe it's true, maybe it isn't true. But for every value that I've looked at, this is his words now in 1919 or whatever it is, for every value I've looked at, the sum is non-positive. The other way around. Non-positive, yeah, less than or equal to 0. So you might say, okay, well, that's interesting. Now, it turns out if that were true all the time, which it's not, but if it were true all the time, then that would give you everything and then some. It'd give you everything you like the Riemann hypothesis and all the zeros of the zeta function are simple. That's good. And it also gives you stuff you don't like, and that's bad. The stuff it gives you that you don't like are that all the zeros of the Riemann zeta function, the non-trivial ones, are somehow linearly dependent in a kind of first year linear algebra sense. Like maybe, what's the first one? I don't know. 14 point something, a half plus 14 point something I, and the next one's a half plus, I don't know, 21 something I, or whatever. So linearly independent meaning there's some crazy numbers. So like 1,050 times the first one minus 912 times the second one equals 0, say. So these kind of conjectures, they give you everything, but too much. They give you things you want to be true, like Riemann hypothesis, simple zeros, which any person with 2 legs and a heartbeat thinks is going to be true. But it gives you stuff which you think, dang, that's too much. I don't want those zeros to be linearly dependent. That's insane. No one on this planet would think that would be true. So these so-called conjectures, they're kind of interesting in that they can be reformulated in terms of stuff that we're interested in, Riemann hypothesis, simple zeros, linear independence, etc. But what drew my attention to it was the other conjecture. So this so-called Tehran conjecture. So what did I say Polio's one was? You do a whole bunch of sums of lambda of n. Okay, and it's supposed to be non-negative. No, the other way around, non-positive. Whichever way it's supposed to be, that's the way it's supposed to be. It's supposed to be of some sign. I haven't had breakfast yet. What do you want from me? Yeah. So the Tehran conjecture is something similar. It's sums of lambda of n divided by n. So it's like a weighted sum, say. So you do it in your head. Lambda of 1 over 1 is 1. Lambda of 2 over 2 is minus a half, etc. So when you do that, and you do the first 10 values or the first 100 values, and if you're like me, that's all you can code up into a computer before you start swearing at the keyboard. But if you're cleverer than me, you code it up and you do it for the first however many values you like. And you see then that the sum looks to be non-negative. So, and again, just like the so-called Polio, and I say so-called because neither Polio nor Tehran gave this as a formal conjecture. They said, this is interesting, someone go and investigate it. So the so-called Tehran conjecture then is that the sum, n up to x of lambda of n over n, ought to be bigger than or equal to 0 all the time. And just like the so-called Polio conjecture, this also gives you everything you'd like, and in fact, too much. It gives you Riemann hypothesis. It gives you simple zeros. That's great, but dang, it gives us the fact that the zeros are linearly dependent. And that's too good to be true. That's just crazy. So this is the thing that attracted me to the problem. Okay, it was kind of interesting. And then I got to learn about Ingham's results, and I got to learn about this, and linear dependence. It's all good, fun stuff. But this is the question that I kept coming back to. Why is it that one of these sums is supposed to be negative and the other one is supposed to be positive. Why is that? I don't know. I mean, the proof works just as well. Like if, say, the Polio conjecture, the sign were flipped, and from some point onwards, it's supposed to be positive. That also gives you a real hypothesis and everything else. So it's not as if it has to be that it's less than or equal to 0. The proof would work just as well if it was flipped the other way. So why? I've got two sums that are very similar. Why does it look like one's positive and why does it look like one's negative? Well, there's two answers. The short answer is it just is. You know, you just compute the first 1,000 values and it looks like it's negative. Yeah, okay, fine. But that didn't really satisfy me. And the answer ain't that deep. You know, it's the last talk of the day for you fellows in North America. I'm not going to talk about Chebyshev bias, logarithmic densities, any of that stuff. You know, I'm operating on 1 cup of coffee and 0 breakfast, so I can't handle any of that stuff this time of the day. So the answer is somewhat simple. The answer is, well, when you try to approximate a partial sum of something in number theory, I guess you could do a lot worse than use Perron's formula. So what does that mean? It means if you want to know your partial sum, so sum n up to x of your favorite function, like lambda of n, say, then quote unquote, all you need to know is the zeros of the corresponding, zeros and poles of the corresponding L function. Meaning what? Find for me the Dirichlet series whose coefficients are lambda of n, plug that into some Perron's formula. Remember, Cauchy's theorem is a concept. Do the thing, move the integrals, etc. Pull out leading terms, pull out stuff. All right, that's what you do. Now, when you do that for both of these things, I mean, I only have one tool in the shed, and it's that. So I'm going to do that. I say to my sons when I'm teaching them in chess, if you don't know what to do, you've got to do something. Do what you can do. So I guess I'll use Perron's formula. Why not? So when you do that, you find, and this is my sort of layman's interpretation of what's going on. When you do that, it's the same with every other function, like sum of divisor function and so on. When you do that and you play Perron's formula, you get the sum of lambda of n looks like what I would say is a leading term plus a sum over zeros of the zeta function. Okay. When you do the same thing for the Tehran conjecture, you get the sum of lambda of n over n looks like a leading term plus a sum over the zeros. Okay. Now, if you're like me, you say, I have no idea what's going on with sums over the zeros. No idea. The zero, they could conspire, they could get together and figure out all sorts of stuff. It could be the Ides of March all over again on the Senate floor. Conspiracies on conspiracies. It could be crazy. So if you're like me, you more or less throw up your hands at this stage and you say, oh, geez, I've got sums of x to the I gammas, and I don't know how the gammas are distributed, and there should be some cancellation on the unit circle, but I don't know. So if you're like me, you think of those sums over zeros as probably, and erroneously, probably you're thinking of them as error terms, probably. So if that's the approach you're taking, then you're saying, well, these partial sums of lambda of n, we're in Polio territory now, these partial sums of lambda of n, they look like main term plus something that could be an error term, maybe, okay. And that main term is negative. When you look at the so-called Tehran sum of lambda of n over n, it's going like main term, quote unquote, plus a sum over the zeros, which I'm incorrectly but naively taking as the error term. And that main term is positive. So one way of interpreting why is it that it should be that this Polio conjecture, this sum of lambda of n is less than or equal to 0. Why, if I was a betting man, why would I bet on that and rather the sum being positive? Well, in the partial sum, I have a leading term that is negative. It's like, I don't know, 1 over zeta of a half minus 0.6, whatever it is. So some bona fide card carrying, dyed in the wool, actual negative number, 0.6 or something. So minus 0.6. So this so-called Polio sum is going like minus 0.6 plus some crazy sum over the zeros. So one way of interpreting Polio's so-called conjecture is to say, well, probably that sum over the zeros, there can be conspiracies in there, but that won't be enough to overtake this kind of leading term, which is already making the whole sum negative. For you to make the sum positive, you've got to get lots of conspiracies going on in this sum over the zeros. And same, but in reverse for the Tehran sum. Now, I said before, naively and erroneously, everything I do is erroneous. So naively and erroneously, I was viewing this as main term and error term. Now, the reason why that's a crazy way of looking at it is that normally in number theory, the error term is smaller than the main term. That's what we call the error term. But here, the reason why Polio's conjecture is not true, and it's not true, it fails infinitely often, etc. The reason why it's not true is that crazy stuff does happen in that sum over the zeros. So we said before, you've got this sum going like, I don't know, minus 0.6 plus some crazy sum over the zeros. It's reasonable to say maybe the crazy sum over zeros doesn't get too big. Yeah, the thing is that it does though. It gets big enough to swamp that main term. And ditto in the Tehran conjecture, the sum over zeros gets big enough to swamp that main term. So these conjectures look like they should be true because this error term, it could be small, you know, but the reason they ain't true is that the error term can get big. So now, here's my motivation for why I wanted to look at this problem with Mike and with Greg. So, oh yeah, I don't know if I can put something in the chat. Anyway, if you just type in fake news archive, you'll see the article. It's up on the archive whenever. Also, it's the shortest title I've ever had for a mathematical manuscript. So yeah, winning. So here's the motivation. And again, in a very lowbrow sense. I'm nothing if not lowbrow. So if I say the sum goes as a negative term, like minus 0.6, and some crazy sum over the zeros, then reasonably you say to me, okay, well, that crazy sum over the zeros, probably wacky stuff happens and it gets as big as you like, very rarely, but it gets quite big. And ultimately it swamps that main term. Okay, fine. So now I want to make it harder for the sum over the zeros to swamp the main term. I want to give this sum the best fighting chance of the main term outweighing the error terms. So in my sum over lambda of n, my main term is minus 0.6 or something. Now, if that leading term was say minus 1,000,000, and I had the same kind of sum over the zeros, well, I'm sure ultimately that sum will get large enough and it will swamp the minus 1,000,000. But that's going to happen very, very rarely, right? You ain't going to detect a single value of x where there's a sign change ever. So if we could cook up something where the leading term was huge, minus 10, say, then no one on God's green earth is ever going to observe a sign change. So getting back to Polio, say, we do know sign changes in so-called Polio's conjecture, the sum of lambda n up to x. We do know values of x where this is positive. And the first one's at like 900 million or something. And the same in the Tehran conjecture, so-called Tehran conjecture. We know explicit values. There's a value of x for which the sum is negative. Now, just for fun, I would think that the bigger the leading term, the harder the sum over zeros has to work, the more conspiracies that have to take place on the floor of the Senate in order to swamp that main term. So now the problem is we're not saying Chebyshev biases, we're not saying prime number ratio, we're not saying anything like that. We're just saying, can we come up with multiplicative functions, arithmetic functions, lambda, whatever, something that looks like that, so that I can get a whopping large main term, a whopping large leading term. Indeed, can I come up with arithmetic functions, multiplicative functions, where I can find the biggest leading term and then some sum over the zeros? So why the title? Why the title Fake News? Well, obviously is a tribute to the greatest president the world's ever known. There's that for sure. But also, these functions we look at, they look a bit like lambda, and lambda looks a bit like mu, the Mobius function. When n is square free, lambda and mu are the same thing. The only difference is that when n is not square free, mu of n is 0. So again, one of the differences between lambda and n, which is striking to me, again, lowbrow. I'll say the word bias, but I just mean this idea of there's a leading term and there's some error terms. So what's striking to me is that when you play this Perron's formula game, the only game I know how to play, mind you, when you play this game with lambda, you get a leading term and a sum over the zeros. Leading term's negative, and you think, okay, well, I guess it's got a bias or a skew or whatever you want to call it towards negative values. Okay, yeah. When you do the same thing with the Mobius mu function, you put it into the formula, you do the thing, you move the contour, whatever it is you do, you find there is no leading term. There's no leading term. There's just a sum over the zeros. So then you think, okay, well, I guess it kind of hovers around 0, say, or unbiased, or, you know, it's there's no leading term, so there's nothing for the error terms to have to fight against. So why the title, Fake Muse? So we consider two things in the article. Things that are generalizations of lambda, so just taking on pluses and minus ones, and what's the biggest bias we can get there? Can we rig the deck? Can we deal off the bottom of the deck and make a function, just cook up a function that has a massive bias, the biggest bias, and we can do that. And now if we have a function that looks like the mu function, plus ones, minus ones, and zeros, can we cook something up that still has a big bias? Bias again meaning big main term, or something that's close to 0 main term, and we can do that too. So the point of the article kind of closes off, at least for me, closes off an investigation which sort of, I don't know, started on and off back in 2006. And I never really knew what to do with it. I never really was too comfortable with, oh, I guess one of them's positive, one of them's negative. That's the reason. And the reason ain't that deep, but I had to figure out what the reason was. And then talking with very clever people much cleverer than me, Mike Mossinghoff, Greg Martin, talking with people at various research visits, conferences, and the like. Then I said, well, how about this as a problem? I said, oh, that's kind of interesting. Can we cook up examples where this is true? And we did. So, well, I guess we're making some revisions to the article now. It's still up on the archive. Again, just type in Fake Muse and my name or Mike's name or Greg's name or archive, and it'll come up. So one kind of parting word then, while I finish, one parting word. I don't know if now's the time for inspirational speeches, but one parting word would be to the young people in the audience. I don't know if I'm still a young person, but to the young people in the audience, that sometimes when you're doing your PhD, say, you come across a problem, you don't really know what to do with it, but it's kind of funky, kind of interesting. And you kind of write it down in a little diary somewhere, and you kind of come back to it every now and again. But it has been a fun experience working on that on and off over the last few years. And I'm very grateful to Greg and to Mike for providing the muscle and the brain power for us to bring this to a conclusion. So I thank them, of course. And I just want to conclude by saying thanks again to Mel. Thank you to the people in the audience who turned their cameras on, so I have an actual audience. Hooray! Thank you very much, and please enjoy the rest of the conference.
Thank you. Okay. Any questions for our speaker? So it's 7 a.m. in Australia now?
Yep, 7:25 here in Canberra, the nation's capital.
I see. And let's see. David Ross had been there. I think he just left.
I'm still here.
In Hawaii.
Oh, Kevin, Kevin, you put it in the chat. Good on you, man. I was trying to do that before, and then I was saying best for me not to move the mouse around because I might close meeting for all or something. No one wants that. Yeah.
No worries. I got you.